linearize the developed model, nonlinear model. And for that, at the beginning, just for simplification, we are assuming that the volume is constant. Now, if volume is constant, from this total mass balance equation, we get Fi equal to F. You see, if we substitute here dV dt equal to 0, volume constant means dV dt equal to 0. In that case, this first equation is Fi equal to F. And that is what written here, Fi equal to F. Now, the stepwise fashion, this mechanism is shown. I mean, we are just starting from linearization by the application of Taylor series till the representation of the linearized model in terms of deviation variables. Okay. In the following, all sequential steps are shown, starting from the linearization of the model by the application of Taylor series expansion to the representation of the linearized model in terms of deviation variables. If volume is constant, our model, CSTR model, gets this form. You see, if volume is constant, our CSTR model gets this form. If volume is constant, our CSTR model gets this form. So what is tau here? Student, anyone? What is tau?
Sir, V by Fi.
B by Fi, and that is called what?
So time constant.
Any better term? Residence time. Okay. This is residence time. And what is ACE? What is the expression for ACE? In the second equation, you see last term, ACE is there. What is the expression for ACE? One 0040 Sahil. Sahil is there. 10041 Sai Kiran. Anyone? What is the expression
minus
for ACE?
delta H by rho Cp.
Yeah, correct. What's your number?
30030.
Yes, you see, ACE equal to minus del H divided by rho Cp. Okay. Now, can anyone tell which one is a nonlinear term in these two equations? See, this is the model structure now. If we consider volume constant, we have two equations, and these are the equations. Now we want to linearize the nonlinear term. So before that, we need to know what is the nonlinear term involved in this model structure. Anyone can tell what is the
So that
nonlinear?
exponential term is nonlinear term.
Yeah. Anything else? Anyone can tell the correct answer? What is the nonlinear term involved in this model structure? Rahul Goldar 10031. Rahul Kunawat 10032. Rahul Kunawat 10032. Rahul Nath 10033. Rahul Nath 10033. Anyone else can tell?
Sir, CA into e power minus e by RT, because
Correct.
both of them are in the.
Yeah, correct.
Yes.
What's your roll number?
So 30036.
Yes, correct. This is a multi-input, multi-output example. Okay, under that we are considering this CSTR example. So naturally we can expect there are more than one nonlinear term. So these are the two nonlinear terms. CA into exponential of minus C by RT. Fine. Now, can you apply the Taylor series on these two terms and let me know the terms? So we have identified the nonlinear term, that is CA into exponential of minus C by RT. Now we want to linearize these two terms first. I mean this term first by the application of Taylor series. So apply the Taylor series on this term CA exponential of minus C by RT and let me know the terms. Carry on. Shivam Raj is there 10050. Shivam Raj. Subhajit Bagh 10054. Subhajit Bagh 10054. Shukda Prasad Murmu 10056 is there. Shukda Prasad Murmu 10056. Sankar Patni 10046. Sanskar Patni 10046. Ravi Kiran 30016. 18 C is 30016. What I asked to do?
Apply Taylor.
Yeah. Doing?
Yes, sir. Yes, sir.
Okay, carry on. One triple 001 Avilas Sinha. 10001 Avilas Sinha. 10003 Adarsh Kumar. 10003 Adarsh Kumar. 10005 Aditya Agarwal. 10005 Aditya Agarwal. 10006 Aditya Chawla. 10006 Aditya Chawla. 10007 Adrija Roy. 10007 Adrija Roy. 10008 Akshay Agarwal. 10008 Akshay Agarwal. 10010 Ankit Bharma. 10010 Ankit Bharma. 10011 Arjav Rastogi. 10011 Arjav Rastogi. 10013 Abharu Badri Bishal. 10013 Bishal. 10014 Ais Akhtar. 10014 Ais Akhtar. 10015 Devesh Govind. 10015 Devesh Govind. Jyotiraditya 10017.
Yes, sir.
Done.
Sir, I got 3 terms. Then it should be, first term would be a constant, that would be the e to the power minus capital E by RT naught, and then multiplied with CA naught if we
Correct.
take the first term. And then again the same term that would be multiplied with CA T minus T naught, and then there would be again e to the E by RT naught square.
Yeah, you see it is matching or not. I'm showing now.
Okay.
Just let me know that it is matching or not. 10018.
Yes, sir.
Got these terms?
Sir, I'm Jyotiraditya 10017.
You
It
got
was
it.
matching, sir.
Okay, good. 10018. Kausal Jagdish. Okay, fine. Anyone else got the result? Linearized version of the term?
Yes, they are matching.
Yes, sir.
Matching.
They are matching.
Correct. Correct. Now what we'll do, we will just substitute here in the model equation. Okay. Next we will do, in the next step, we will substitute this linearized term in the model equation. Then we will take the steady state form of that model. Then by subtracting, we will get the final equation, linearized model in terms of deviation variable. Let us follow these steps. So next we want to substitute these linearized terms in the model equation. You see the model equation. First I have substituted in the first equation, that is component A balance equation. Followed by energy balance equation, you see. I mean, now it is quite straightforward. Just, although it looks quite complicated, but it is just a substitution, nothing else. 10020 is there, Lalit. 10020, Lalit. 21, Mausam Sinha. 10021, Mausam Sinha. Please let me know if my equations are correctly written. Let me know if my equations are correctly written.
Yes,
Anyone? Are they fine?
Yes, sir.
Okay. So this is the third step. Now, what is the next step? Anyone can tell?
So probably we will be modeling it for steady state.
Yeah, steady state. Yeah, we want to represent the equations at steady state. What's your roll number?
Sir, 10052, Siddhant Kumar.
Yeah, correct. See, I have written the equations in steady state. I have written the equations in steady states. So naturally, this t minus t naught and multiplied terms, it gets vanished, because at steady state t minus t naught is 0. It becomes basically t naught minus t naught. Similarly, at steady state, this Ca minus C naught, that becomes basically 0, because Ca minus C naught is Ca naught minus Ca naught at steady state. So the last term also gets vanished. Okay. So last two terms get vanished. Accordingly, we write the steady state model equations represented by equations 3 and 4. Accordingly, we write the steady state model equations represented by equation 3 and 4. Equations 3 and 4, are they matching? Anyone can
Yes.
confirm me? Matching?
Yes, sir.
Okay.
Yes.
So what is the next step?
We
Anyone?
will like we can write it as d of Ca minus Ca0. Similarly, like we can subtract 1 and 2, 1 and 3. and
Correct.
2 and 4.
Yeah. Roll number?
30018.
Yeah. Correct. You see, we are going to subtract because we would like to represent the linearized model in terms of deviation variable. Now you would like to subtract the steady state model from the linearized model, and we can get the linearized model equations in terms of deviation variables. See, after subtracting, I have written directly the linearized model equations in terms of deviation variables.
So where did this CA prime terms come from?
CA prime or
CA
CAI?
prime, CAI prime. Yes, sir. Means these were not in the original equations.
CAI is there?
Yes, sir.
Yeah, then somewhere CAI minus, you see this one? Here
Okay.
CAI, not here CAI, this one.
Yes, sir.
So anyhow, CAI minus CAI not should come.
Yes.
Okay, like CA minus CA naught would come. In fact, that is there. CA minus CA naught, T minus T naught. Yes, you just check and let me know whether you are getting or not finally. Three triple zero one, Abhishek Kumar.
Yes, sir.
Yeah, what is your status? I mean,
Yes, I'm currently like calculating the deviation variables.
okay, carry on. 3002, Achal Kumar. 3002, Achal Kumar. 3004, Sai Kiran Nayak. 3004, Sai Kiran Nayak. 3009 is there. Girija, BMS Girija. 3009. 30010, Padma Sri. 30010, Padma Sri. 30011, Paulami Chaudhary. 30011, Paulami Chaudhary. 12, Pratik. 30012, Pratik. 30013, Pratik Kumar. 30014, Rakesh Gowda BT. 30014, 3015, Rohit. Rohit is there. 3015. 3017, Sayan Haldar. 30017, Sayan Haldar. Yeah. Anyone? These equations are matching?
Yes, sir. The first one is matching. I'm still doing the second one.
Okay. Carry on. Three 3019, Sasank Gautam. 30019 Sasank Gautam.
Yes, sir.
What is the status?
I am doing the second one.
First one is matching.
Yes, sir.
Okay, good. Carry on. 30020 Sivans Raj. 30020 Sivans Raj. Let me know if anyone got both the equations.
Yes, sir, they are matching.
Matching? Okay,
Yes.
good. Good. So I think these deviation variables you have considered. You see? These are the deviation variables. Okay? Who else got the equations?
Yes, sir, they are matching.
Matching? Good. Anyone else got the results?
Yes, sir, matching.
Good. Good. So this is the multi-input, multi-output example. So basically, if the model is nonlinear, we can linearize the model structure using the Taylor series expansion. Fine. But remember, it does not mean that we will go for this linearization, because nowadays there are, numerical methods available for solving the nonlinear equations as well. Fine. I repeat, we have started how to linearize the nonlinear model, and finally we can represent in terms of deviation variables. But it is not indicating that all the times you linearize the nonlinear model of the given system and you go for control. Okay, because this is quite old concept. Nowadays we have efficient, elegant tool, numerical tool especially is available to solve the nonlinear equations, nonlinear algebraic equations, nonlinear differential equations. For all of them, numerical methods, even the many softwares are available. Anyway, now our next topic is transfer functions. Okay, you see in the first diagram in the left hand side, we have drawn a block which is representing a process. Then obviously for a process, there is input and there is output. In the left hand side, we have first drawn a process through a block. And for a particular process, we know there is input and output. Input we are denoting by F and output we are denoting by Y. Okay, so this is in time domain. In the second figure, you see the same thing we have drawn, but it is in Laplace domain S. The same left-hand figure we have drawn in the second figure, but it is in terms of It is in Laplace domain. Fine. Now you see this input function we can transfer in terms of output function, that is y, or output variable y, with the use of transfer function, that is we are representing by g within bracket s. This TF is transfer function. Transfer function is represented by g within bracket s, that is the output in Laplace domain divided by the input in Laplace domain. Fine. This is the transfer function using which we can transfer our input variable to output variable y. So transfer function TF, as I told, it is represented by capital T, capital G. It is basically the output divided by input in Laplace domain. Okay, so this example is considered for a CISO process, single input, single output process. This is the example or the simplest example, and this is a single input, single output process. Okay, now let us consider how to formulate this G for a single input, single output system. We want to now study how to formulate the transfer function for a single input, single output system in a general way. In a general way. So for this, we consider a single input, single output general equation, you see, which is represented by equation 1. We are considering a general nth order linear or maybe linearized system equation. Can anyone tell why this is single input, single output system? Equation 1. Why equation 1 is the representation of a single input, single output system? Anyone? Yes. Why equation 1 is the representation of a single output, single input, single output system? Anyone? You see in this equation only one output y and one input f are present. So that's why it is single input, single output system. Single input is f, single output is y. Okay. So both ft and yt are deviation variables. Here both the input f and output y are in terms of deviation variables. That means y within bracket 0 is 0. If y is deviation variable, so y instantaneous minus steady state y equal to 0. And within bracket 0 means this is steady state. Within bracket 0 means this is basically time t equal to 0. And time t equal to 0, we are considering steady state. So at steady state, the deviation variable y is 0. I repeat, if y is deviation variable, we can write y equal to y instantaneous minus y naught. Now at steady state, y instantaneous and y naught, they are identical. That's why y at steady state t equal to 0 becomes 0. Now if this is 0, naturally the differential terms are 0. Accordingly, we can write the differential Laplace transform of the nth order differential in this form. Accordingly, the Laplace transform of the nth order time derivative is represented by this equation. Okay. Laplace transform of the nth order differential becomes s to the power n y bar s. So I have written the Laplace transform of nth order differential only. The rest I did not show. With this understanding, we'll go back to equation 1 now. With this understanding, we'll go back to equation 1. So you see equation 1 yields this. With this understanding, our equation 1 gives this form of equation in Laplace domain, the last equation which is shown. Fine. Now you want to write the transfer function. What is transfer function? This is the transfer function, you say. Transfer function we denote by capital G, that is y bar s by f bar s. Now if we rearrange the last equation, this one, we get this form. If we rearrange this equation, we get this form of transfer function. Is this clear to everyone? How to derive the transfer function for the simplest single input, single output system?
So why do we need to find this transfer function? What is the meaning of this function?
Yeah, we are coming to that gradually. Okay. So let me give the answer briefly. So ys divided by fs equal to this. Okay. Now what we do, fs, if you recall, there are 4-5 types of changes we have considered: step input, pulse, impulse, ramp. So we will accordingly make some change in this fs. Okay, in Laplace domain. Then we will take the inverse of Laplace transform to find the y. I repeat, the transfer function for a particular process is given to you. Then you are asked to find the y in time domain against a supposed step change. Okay, transfer function will be given to you and you will be asked to find the y in time domain against a step change in f. It is somewhat like this, just to find the process dynamics against a certain change in the input variable. This is the use of transfer function. Suppose fs is given 1 by s. So what will be ys? This gs multiplied by 1 by s. Then you take the inverse of Laplace transform to find yt. Okay, then you will get the expression for yt. I repeat, this transfer function will be given to you. And suppose you are asked to find y in time domain against a change in, suppose, step change. That means f bar s is 1 by s, if you consider a unit step change. So y bar s equal to this transfer function multiplied by 1 by s. In the next step, we need to find the y in time domain. So you take the inverse of Laplace transform and find yt expression. So by this way, we can basically know the process dynamics against a certain step change or certain change in the input variable. Anyway, we'll consider this in details. Now you see there is a multi-input single output system, MISO system. In the next step, we are considering multi-input single output system. So obviously this figure is showing that we have two inputs, one is F1, another one is F2, and we have single output, that is Y. We have two inputs, F1 and F2, and we have one output Y. So we have modified the linear or linearized model little. You see, in the right hand side, just we have added one extra term that is associated with our second input F2. We are continuing with the same linear or linearized model. Just one additional term is added in the right hand side, you see this one, which is associated with our second input F2. Can you quickly find the transfer function for this and let me know the transfer function of this model? Student, equation is given just by the similar way as we followed for single input, single output system. You find the transfer function and let me know. Quickly do it. For this MISO system, you let me know the transfer function for the process.
Sir, it'll be B1 F1 T plus B2 F2 T by AN S to the power N plus AN minus 1 S to the power N minus 1 and so on.
Yeah, you represent in terms of Laplace domain. Okay, you are correct, but you have to represent in Laplace domain. Transfer function is all the times in Laplace domain only.
Yes, so like in terms of S, F1 bar S and all.
See, it's matching or not now. I'm showing you.
Yes, sir, yes, sir.
What's your number?
19CH10037.
Yeah. Are you getting anyone else?
Yes, sir.
Good.
Yes, sir, it's coming.
Coming. Correct. So you see there are two transfer functions then for this case. Okay, this is G1 which is associated with F1. This is G2 associated with F2. Okay, and we have one output only. Now finally, one thing you are usually asked, that is to develop the block diagram. You see the block diagram for this meso system is shown in the left hand side. I think there is no difficulty to understand it. We're just adding these two. I think you are not facing any difficulty to understand this block diagram. Okay, so this signal is basically F1 G1 and this signal is basically F2 G2. We are just adding these two and getting Y. I repeat, this signal, this is the output. Output is basically input multiplied by transfer function. So this is F1 G1 and this one is basically F2 into G2. If you see the definition of transfer function. Now F1 G1 is added with F2 G2 and we get Y. That is what we got here, you see. In a similar fashion, if we have n number of inputs, then we get the block diagram which is shown in the right hand side. If we have total n number of inputs, here we have considered two inputs F1 and F2. Now suppose we have n number of inputs, although our output is only one, Y. But inputs are F1, F2 to F suffix small n. Then we have this type of block diagram. Clear?
Yes, sir.
Good. Now I am giving you, we do not have much time, but I am giving you a simple problem. Okay, I think you can do it quickly. This is the example system, you see. We want to apply now this transfer function concept to this simple system. We want to apply this transfer function concept to this simple liquid tank system. And I am showing here what you need to do in stepwise fashion. We have adopted a simple liquid tank system, and I am just showing the sequential steps that you need to follow. So in step 1, we need to develop the model. For this liquid tank system, we have already developed the model, and that is a linear model. You see in the general formula I have written either the model is linear or linearized. So here our model is linear model, so no problem. In the second step, you need to write the equation in terms of deviation variables. This we need to do, otherwise you will face the problem when you are going to take the Laplace transform of the differential. Okay, we are taking this, we are converting this equation, model equation, in terms of deviation variables, because you are understanding when we are going to take the Laplace transform, we will face problem. I mean, many more terms will come. That's why to make it simplify, we are considering in terms of deviation variables. Prime symbol is present, you see, over the variables only. So can I write this transfer function model after taking Laplace transform?
Yes, sir.
Good. So you can write the transfer function model in this way. So step third, you formulate the transfer function model. So for that, simply you need to take the Laplace transform in both sides of the linearized model represented in terms of deviation variables. If you get this, then it's easy to develop the block diagram, you see. We are developing the block diagram now. And these signs you are understanding. This is positive because this is input variable Fi, and negative sign is associated with output variable because these transfer functions are same. You see 1 by as and here also 1 by as. Only difference is represented through the sign. Obviously, this is input, so it is positive, and this is output, that's why it is negative. Physically also we are understanding, and equation wise also we got this this block diagram. Is this fine, student?
Yes, sir.
Good. Okay, bye bye then. Thank
So
you.
when is
Yes.
So when will be the first test conducted? Because the test window is from 6 to 10 September.
Yeah, then we have to follow that, no? I will let you know. Okay, I'll send one email, separate email to all of you.
Thank you, sir.
Yeah, thank you.
Thank you, sir.
Thank you to everyone.
Thank you, sir.